Welcome to a tutorial on the 8085, and here we're going to learn about writing a program of 8-bit addition which is going to generate a carry. So let's say we have got two data. So one of them, let it be, well, let's say 05H, and the other one, let's just be, well, FFH. Okay, so this is our first data and this is the second. Okay, now if we need to add these two up, okay, so first we need to convert them into their corresponding binary forms. So for 05H we got 4 zeros and then 0101, and for FF we got it as all ones. Okay, there you go. Now if you just go forward and add them, you're gonna get this sort of a result. Okay, so now we can see that the result is larger than 8 bits. Now this means that it has basically generated a carry bit. Okay, so there you can see the carry bit being generated. Okay, now the result, I mean the 8-bit result that we have over here, this is a lower nibble, and there goes the upper nibble. Now the lower nibble is equivalent to 4 in hexadecimal, and the upper nibble is equivalent to 0. So the result of addition of these two numbers is going to produce a result of 04H. Okay, that's in hex, and it's going to generate a 1 carry bit. Okay, so we are going to have a carry right now. Now you need to keep in mind that whenever there is a carry bit being generated, now if we just write a program, okay, with of 8-bit addition, that is, now in that case, if this program contains the data, I mean these two datas correspondingly, then in that case we're going to have a carry generation. Now if in 8085 systems there is any carry bit being generated, then let me remind you of the carry flag. Okay, so this is basically the carry flag I'm just talking about over here. Okay, so there it goes. This is the carry flag bit. Okay, let's see why. Now this carry flag bit is going to be set to the logic 1 level. So at that moment we call that the carry flag is being set whenever there is a carry. So if we monitor this particular condition in our program, then we can write a program that that can basically monitor whether there is a carry bit being generated or not. Okay, so let's start with our program, but first let's just assume that our address range, okay, lies from 0000H to, let's say, 3FFH. So this is going to be the memory address range of the system, okay, that we have just written the program for. So this is the memory address range of our system, okay, and we're going to write our program keeping in mind this particular range. And now since we are going to having these two data stored already in the memory, external memory chip, that is, so let's say that these two data are stored in the corresponding memory location, let's say 1000H. so this is where the data 05H has been stored. Okay, and the data FFH, let's say it's just stored in the memory location 1001H. Okay, so now keeping in mind, let's just divide it into columns. Okay, there you go. Now the process of writing such a program is, the beginning part at least, is just the same as the previous tutorial, the example shown in the previous tutorial. So we're going to start here by loading these data from the corresponding memory locations into the registers of the 8085 microprocessor. So since we're loading it directly from the memory, we need to keep in mind that we need to load these data in the accumulator first, and then we can move it into any of the other registers. So we're going to be using the registers A. Okay, we need to use that, of course, and we're going to be using an another general purpose register, that is the register B, okay, to store the corresponding operand datas respectively. So we're going to write here the suitable opcode, of course. So we're going to write here first MVI, okay, and then load a data byte of 00H in the register C, basically. Now I'll tell you why I did that a little later, but first we're going to just write the program down. So next we're going to be loading the data from the corresponding memory locations. Okay, so here the first data is present at the location 1000H. Okay, so I'm going to write here LDA, okay, 1000H. There you go. And we should also keep in mind that, well, we've just taken here, for example, that our program will begins from the memory location or the memory address 0000H. Okay, so after that, after I just finish writing the program here, I'm just going to give the entire memory address range which the program basically consumes. Okay, so now that we have just loaded the data from the corresponding memory location 1000H, now we can basically see that the accumulator would contain the data 05H. Now we need to load the next data also. Now it will only be loaded in the accumulator, so we need to move this data 05H into the register B first. So we execute the move instruction, move B comma A. Now that just sends the data into register B. Now we've seen that in the previous tutorial, of course. And now once again, LDA 1001H. Now this time the register A is going to have the data FFH. Okay, so now that both the datas are loaded, okay, now what we need to do is that we just need to add them up. So we just go forward and, well, execute the add instruction. So add B. There you go. So after the addition is over, the register A will have the result. Yeah, there you go, 04H stored in it. So this is basically the result of this addition process that we had exhibited right over here. So this is exactly the result that we have stored in register A. So now register A basically stores it, and also the carry flag is set right now. Okay, so we need to monitor for the carry flag at this particular moment, whether there is a carry bit being generated or not. Okay, now in order to do that, we are going to be using a conditional jump statement. Okay, we're going to be using a conditional jump instruction. So let's just go over here. So after the add instruction, we use the instruction JNC. Okay, JNC. Now here JNC basically stands for, since it's a new instruction that you're learning, JNC stands for jump on no carry. So in this conditional jump statement, okay, the condition is true whenever there is no carry, and if there is carry, then this condition is basically false. So we're actually using this particular jump statement in a way that if there is no carry, the program would just ignore the necessary things that it should do if there is a carry, and then just jump onto some different basically transfer the control to some different memory location and fetch the instruction from over there. Okay, as if there is no carry, so it doesn't need to monitor all those conditions. So that way we're just using the program. So the syntax goes this way: you need to write JNC and then give the target memory address where the program control needs to be transferred, and this address is of course a 16-bit data. Okay, so here, since we don't know that which address it should jump to, since we haven't given all the memory addresses, so I'm just gonna designate this the area where the program control should transfer to with a level J1. Okay, so this is basically a level that I've just used over here, a level marker, you can say. So after that, let's just assume that there is a carry, and this statement, the condition of this jump statement becomes false. So in that case, the program would just move to the corresponding the immediate next line. So if there is a carry, what the program should do? Okay, it should basically increment the contents of its register C. So we're going to write here INR C. Now here INR actually stands for increment, okay, or more precisely increment by 1. So the syntax goes this way: you'd write INR and give the name of the specific register. Now this is basically used in order to increment the contents of a specific register by 1. So here, since we have loaded this particular number that you can see 00H into the register C, so whenever a carry is detected, okay, we're using the increment instruction, the INR instruction, to increment the contents of the register C by 1, so that the register C now stores, okay, 0 1H, okay, in order to indicate that a carry has been generated. Now this is basically done in order for the fact that, well, it's not directly possible. I mean, there is no instruction in the 8085 instruction set to directly display the contents of the carry flag bit, okay. So in order to counter for that, we have to write a program this way so that we can at least display that there is a carry. Okay, so we use a conditional jump statement and a general purpose register to actually execute the process somewhat this way. Okay, so after that, after we write the increment instruction, now that we have just done the needful, okay, what we need to do is that we need to store the result. Okay, and let's say that we store the result of the addition in the memory location, let's say, yeah, 1002H. So this is where we're going to store our result of addition. Okay, and we're also going to store the carry bit. Okay, so if we need to monitor whether there is a carry bit or not, we're also going to store the carry bit in the location 1003H. Now if you directly check the location 1003H, if there is a 1, then you know that there is a carry, and if there's a 0, you know that there's no carry bit being generated. Okay, so now we're going to store the result in 1002H. So there you go. We're going to write here STA and give the location, that is 1002H. Okay, so there goes our result, and now we need to also store the carry. So we need to move the contents of the register C into A. So move A comma C, and after that we're going to write the STA command once more. Now this time we store the carry bit in the location 1003H, and finally that just brings us to the end of our program. Okay, so now that we have just written the program successfully, let's just, okay, now this particular level, that's J1, actually, well, is the level of STA. Okay, so I'm just going to write that down over here. So here we're going to transfer the control if the condition is false for monitoring the carry bit. Okay, so now let's just go on to putting down the hex codes over here. So for MVI, the hex code would be well, 0E. There you go. And next, now since you should always keep in mind that the memory chip, the external memory chip, actually contains 8-bit registers. So each of the hex codes that I'm just putting down over here are 8-bit hex codes. So 0E actually corresponds to the hex code for this instruction MVI-C. Okay, and next we need to store the data. So this is also an 8-bit data, so we need to store it in a different register immediately next to where we have stored the data 0E, which of course, you know, corresponds to an opcode. Okay, so we store 00 in the immediate next memory register, and next we got the instruction LDA, whose hex code is 3A. Okay, and now we have a memory instruction, I mean memory location, which is actually 16-bit data, and in order to store this into 8-bit registers, we need to break it up into groups of 8, 2 groups of 8, that is. We have the lower 8-bit, that is 00, we first store it, and then the higher 8-bit, we store it next. So this is how we supposed to store a 16-bit data into 8-bit registers. Okay, now for move B comma A, we got, well, let's just check it out. For move B comma A, the code is 47. Okay, next we got LDA, there it's 3A once again, and we got a memory location. So again, divide into 2 groups of 8 bits, store lower 8-bit first, next the higher 8-bit. And then for add B, the code, I mean the hex code is 8T. Okay, for J and C, the code's gonna be, yeah, D2. Okay, I'm going to write here D2, and then we need to keep 2 spaces blank, because here J1 actually denotes a memory location where the program control is supposed to transfer if the if this statement, the conditional over here, is true. Okay, so we just keep these 2 positions blank, and now for INR C, the code is basically 0C. Okay, and then for STA, it's 32, and now again there is a memory location, so we divide it into groups of 8 bits, lower 8-bit and then higher 8-bit. Okay, and for move A comma C the code is going to be 79, and once more we have an STA command, so 32 again memory locations, so divided into groups of 8 bits, so lower 8 bit first, higher 8 bit next, and for halt the code is 76. Okay, so now that we've just written down the hex code successfully, let's just give the corresponding memory locations also. Okay, so there's our corresponding memory addresses. Now we need to finish the unfinished business right over here. So we can see that the level to which the program control is supposed to transfer for the jump statement is actually the level where the STA instruction lies. That is designated by the term J1, and for that the corresponding memory location is actually 000E. Now we need to write 000E instead of J1 just beside the J in C statement. Okay, so I'm just gonna wrap this out for now, and well, I'm gonna write here 000EH. Okay, so this is actually indicated by the level J1, right? So since this is also a memory location, so we need to divide it into groups, 2 groups of 8 bits basically, and then store the lower 8 bit first and the higher 8 bit next. Okay, there it goes. So the program control is supposed to transfer to this memory location, that is 000E, once this condition becomes true. So that goes our first program over here. Now if you just take a better look at this program, then you can basically see that this program has consumed a total memory space of 22 bytes. Okay, starting from 0000H to and continued till 0015H. Now for 8085 systems, we need to keep the memory consumption at the most minimum level as much as possible, because in such systems there is always a question of memory crunch. So we are gonna try and write the program once again and reduce the entire memory consumed. Okay, so there's our columns concerned. So now we are gonna start writing our program over here. So first up, once again we write MVI. Okay, so begin with the MVI command, so MVI C comma 00H. Okay, and now after that we are going to use a new instruction over here that is designated with this, that just is known as LXI. Okay, now this stands for load register pair immediately, and the syntax goes somewhat this way. We're going to write here LXI, then give the name of the register pair and then the 16-bit data which we are supposed to load into the register pair. Well, actually this instruction, what it does is that it just treats 2 registers as a pair, and that just helps us to store a 16-bit data, okay, using 2 8-bit registers. So if we're gonna write here LXI H, then this actually stands for the HL register pair. Okay, so if we're gonna write here LXI, if we're gonna write here LXI H, then this means this means the HL register pair. Okay, so if we just write the command this way, LXI H comma 2001H, okay, then it'll just load this, it'll just divide 2001 into 2 8-bit groups since it's a 16-bit data, and then load the H register with the higher 8-bit, okay, and L with the lower 8-bit. So now you can see that how we can just use 2 8-bit registers and store a 16-bit data together. Okay, so this instruction, it just takes 2 registers, as the name is specified over here, as a register pair, okay, and now it stores 16-bit data. So if we write LXI H, then this just means the HL register pairs. If we write LXI B, then this would mean the BC register pairs, okay, and if we'd write LXI D, then this would correspondingly mean the DE register pairs. Okay, so that's how you can use this particular statement over here. So here we're just using the HL register pairs, so we are gonna write here LXI H, okay, and we're just loading the HL register pairs with the memory location 1000H. So this is actually the memory location where the first operand data is present. Okay, so after that we just move forward to our next instruction. So we are gonna actually transfer the data present in the location 1000 and H to the accumulator. So we're gonna use the instruction, well, move, okay, A comma M. So this particular instruction, that is, well, move move A comma M, well, this actually means move data from the memory location stored in the HL register pair into the accumulator. Okay, so this M is actually used to designate the corresponding memory location that is stored in the HL register pair. Okay, so now that we know this particular memory location, that is 1000H, it just contains the data 05H, which we're supposed to load it into the accumulator. Okay, so now that the accumulator is loaded with the data 05H, so let's just make boxes over here. Here's the A, and then again we have the register B. Okay, so now that we move into our program once again, we're now going to use another instruction over here. Okay, a new instruction, that is INX. Okay, now this means increment the contents of the register pair specified by 1, and we're supposed to write the syntax this way, that INX, and then give the name of the corresponding register pair. So here we're going to use the INX statement, that's a command, to increment the contents of the the HL register pair, so that we can access the data from the next memory location, okay, that just comes after 1000H. Okay, so we are gonna write here INX H. Okay, so that just increments the HL register pair content. So now, since we had actually stored in the HL register pair the data of 1000H, okay, now after the INX statement is executed, this 1000H just becomes 1001H. Okay, so now that the content of the HL register pair has been advanced to 1 more, so what we do is that we just transfer the content. Now HL register pair contains 1001H, so we transfer the data from that very location, or rather, let's just do it this way. We can directly add the data present in the location 1001H to the data present in the accumulator. Now here I'm going to introduce you to the memory related add operation. So we can write here add M. Okay, so actually this particular command here, that is add M, actually means add the data present in the corresponding memory address stored in the HL register pair to the data that has been stored in the accumulator. So whichever data is present in the accumulator, that is basically getting added to the corresponding memory, to the data that is present in the corresponding memory location that has been stored in the HL register pair. So simply speaking, now the HL register pair stores the memory location 1001H. Now we need to remember that 1001H is storing the data FFH currently. Okay, so now that 05H is present in the accumulator, okay, now we are not using the register B in this case. Okay, so what we are doing is that we're just directly adding from this memory location the data FFH to the accumulator. Okay, so after the add instruction is executed, the accumulator content is basically, yeah, there you go, it has been changed, and it's just storing the result of the addition process, that is 04H, and also the carry flag has been set. Now we need to write the code for monitoring the carry generation, and that we can just do it in the very same way that we did previously. Right, so there's our code for monitoring the carry and correspondingly storing the result in the locations 1002H and 1003H. So here 1003H is going to store the carry as in the previous example, and that just brings us to the end of this program. Okay, so now we need to put the corresponding hex codes and the memory addresses. Okay, there's the corresponding machine codes and the memory addresses. Alright, now let's just jump over here. Where's the jump statement? There you go. So now it's supposed to jump to the level J2, which is just over here. So again, it's the same STA statement. Now corresponding to this level, we have the memory address 000C, which we need to put over here beside the JNC statement. So once again, I'm going to write here 000CH. Okay, and now I'm going to divide it into two groups of 8 bits and store the lower 8-bit first, and then the higher 8-bit. So there you go. That's our program that we've just got over here. And now look at this program. It's beginning from the memory address 0000H and continuing till 0013. Now it's basically consists of 20 bytes. Now it's consuming 20 bytes of memory space. That is 2 less than the previous program. So this way we can just use certain instructions and then shorten the program length significantly. So with that, we just come to the end of this tutorial, and we're going to catch up with you next in the forthcoming one. So till then, bye bye for now.